The concept of nothing in physics is not an empty void, but the quantum vacuum state. This state is defined by the lowest possible energy level, yet it is teeming with activity. According to quantum field theory, the vacuum is a dynamic sea of fluctuating fields. These fluctuations allow for the spontaneous, temporary appearance of particle-antiparticle pairs, known as virtual particles. This process is governed by the Heisenberg Uncertainty Principle, which dictates that energy and time cannot be simultaneously known with perfect precision. Over extremely short timescales, the energy conservation law can be temporarily violated, allowing energy to be borrowed from the vacuum. This mechanism provides the physical basis for matter and energy arising without external input, challenging the classical notion of absolute creation, ex nihilo. This quantum foam is the true starting point for modern cosmological models. Virtual particles exist only for a duration inversely proportional to their energy, as mandated by the energy-time uncertainty relation. A high-energy particle pair must vanish almost instantaneously, while lower-energy pairs persist slightly longer. These transient particles exert real, measurable effects, such as the Casimir effect, where two uncharged parallel plates placed extremely close together are pushed toward each other by the imbalance of virtual particles outside versus inside the gap. This experimental verification confirms the vacuum's inherent energy density. The universe's initial state, therefore, requires only the existence of these fundamental quantum fields, not pre-existing matter or energy in the classical sense. The universe began as a fluctuation in the zero-point energy field energy, a self-contained system requiring no external input. The zero-energy universe hypothesis proposes that the total energy content of the cosmos is precisely zero. This is achieved because the positive energy contained in matter and radiation is exactly balanced by the negative gravitational potential energy. Gravity is inherently attractive. To separate two masses requires inputting energy, meaning their combined gravitational field represents a deficit or negative energy. If the universe is spatially flat, as current observations suggest, general relativity implies that the positive mass energy density equals the negative energy density of the gravitational field. Therefore, the universe could have arisen from a state of zero net energy, adhering strictly to the conservation of energy law without needing a creator to supply the initial energy. General relativity describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. The standard Big Bang model extrapolates backward to an initial singularity, a point of infinite density and temperature where the laws of physics break down. However, this singularity is likely an artifact of applying classical general relativity beyond its valid domain. Quantum gravity theories, such as loop quantum gravity, suggests that spacetime is quantized, preventing infinite density. Instead of a singularity, the universe may have undergone a big bounce, contracting from a previous state before expanding again. This eliminates the need for a true beginning point, replacing it with an eternal cycle or a transition phase governed entirely by physical laws.
Cosmic inflation is the period of extremely rapid exponential expansion that occurred fractions of a second after the initial fluctuation. This expansion was driven by a hypothetical scalar field, the Inflaton field, possessing high potential energy. As the Inflaton field slowly rolled down its potential energy curve, it generated a massive negative pressure, causing spacetime to stretch faster than the speed of light. Inflation solves the horizon problem, explaining why the cosmic microwave background radiation is so uniform across vast distances, and the flatness problem, ensuring the universe's geometry is nearly flat. Crucially, inflation magnifies microscopic quantum fluctuations into the macroscopic density variations that seeded galaxy formation. The initial quantum fluctuations, stretched by inflation, became the seeds of all large-scale structure observed today. These tiny density perturbations created regions slightly denser or less dense than average. Gravity then amplified these differences over billions of years, causing the denser regions to collapse into galaxies, clusters, and superclusters. This process demonstrates a direct causal link between the inherent randomness of the quantum vacuum and the highly structured universe we inhabit. No external fine-tuning is required. The structure arises naturally from the interplay of quantum mechanics and gravitational instability acting on a zero-energy background. The fundamental forces and particle masses emerged through spontaneous symmetry breaking as the universe cooled. In the extremely hot early universe, the electromagnetic and weak nuclear forces were unified as the electroweak force. As the temperature dropped, the Higgs field acquired a non-zero vacuum expectation value, breaking the electroweak symmetry. This interaction gave mass to fundamental particles like electrons and quarks. This mechanism shows how complexity and differentiation arise naturally from a highly symmetric, simple initial state, without requiring external intervention to define the specific properties of matter. The laws of physics themselves dictate the transition from symmetry to complexity. If inflation is an eternal process, it leads to the concept of the multiverse, where our observable universe is just one bubble among an infinite ensemble. In this model, different regions of the multiverse could have different physical constants and laws, depending on how the Inflaton field decayed locally. This addresses the apparent fine-tuning of our universe. If there are infinite universes, then statistically one must exist where the constants are precisely right for life to emerge. This removes the necessity of invoking a designer to explain the specific parameters of our cosmos, relying instead on the vastness of possibilities generated by eternal physical processes. The progression from the quantum vacuum to the structured cosmos demonstrates a complete naturalistic explanation for the universe's origin, bypassing the need for a supernatural creator or prime mover. The universe is fundamentally a self-contained system governed by physical laws that operate without exception. The initial state was not absolute nothingness, but a state of zero net energy and maximum quantum potential. The emergence of spacetime, matter, and structure is a consequence of established physics, quantum uncertainty, general relativity, and thermodynamics. The question shifts from who created the universe to how do the laws of physics operate. The answer, based on current evidence, is that they operate autonomously.